Hello, my name is Chase Knutson, and I will be doing lab number 3 on black holes. So the table of contents, we'll be going over the introduction, fundamental physics principles, procedure, tracker analysis, potential errors, and what-if questions. Introduction. What was the lab? This lab investigates the motion of a star orbiting a black hole. A computational simulation was used to generate position data for the star as it moved in 2 dimensions around a black hole located at the origin. The simulation preceded the x and y coordinates of the star over time, creating a unique orbital trajectory. Using this position data, calculations were performed to determine the velocity and momentum of the star at each moment in time. From these values, the rate of change of momentum we use to determine the net force acting on star through its orbit. The second simulation modeled the motion of a moon orbiting a planet and a spaceship launched from the moon. In this model, gravitational forces from both the planet and the moon influence the spaceship's motion, creating a complex orbital path. The purpose of the lab. The main goal of the lab was to use a computational physics method to analyze gravitational motion and estimate the mass of an unknown black hole. By calculating the net force acting on a star and applying the gravitational force relationship, the mass of the black hole could be determined. Another goal was to simulate how multiple gravitational interactions influence motion by modeling the forces between the planet, moon, and spaceship. The simulation demonstrates how Newton's laws can be used to predict motion of an object in systems with multiple gravitational sources. Fundamental physics principle in Lab 3. The gravity. Gravity provides the force that keeps the star in orbit around the black hole and the moon in orbit around the planet. The gravitational force between the two masses given by. The net force on an object determines its acceleration. F net equals ma. If the net force is zero, the object is moving at a constant velocity. This law was used to update the star, moon, and mass spaceship velocities in simulation. And for gravity, we used capital G times mass 1 times mass 2 divided by the radius squared. Procedures. We had to generate motion for the lab using GlowScript. We had to measure properties like the seconds and the star's mass. We had to track the positions using the GlowScript model. We had to extract data also using the GlowScript model and compute the black hole's mass. The tracker output, we had to set the scale. The simulation provided position data in consistent units, so no physics calibration is needed. Align axes, the black hole or the planet. See the X and Y axis along simulated coordinates. Track motion, use the simulation data to obtain the position of the star, moon, spaceship at each timestamp. Interpret data from the position calculation, velocity, momentum, and rate of change of momentum to find net force. Here's the code. Here's the 2 simulations we did. And potential errors. Numerical approximation errors due to discrete time steps in the simulation. Rounded or limited decimal precision when calculating velocity, momentum, or forces. Assumption in the model, such as ignoring other gravitational influences on the star. Initial condition errors like choosing an initial velocity for the spaceship that is slightly off. Visualization limitations, such as the resolution of the simulation affecting perceived positions. What if? What does it mean? The net force on the star is the total gravitational pull from the black hole, while the rate of change of momentum measures how the star's velocity change over time. Parallel and perpendicular components just describe how much of the force or momentum change acts along or across the star's motion. What if? To predict the motion of an entire system, the model must include all gravitational interactions between the black hole and star, planet, and moon. But the strongest influence, the dominant interactions, would have come from the black hole uh, on the star and the planet on the moon, while smaller forces contribute less significantly. Thank you.